Hello everyone. It's time for us to understand a very interesting puzzle called Tower of Hanoi and how it would be solved using recursion. Let's understand the problem statement first and then look at how a solution could be derived for it. So the problem talks about three pegs or rods being given to us, the one that you can see on the screen. And on these rods, there are circular discs being placed. Yeah. So circular discs which have, a provision in between for it to get inside the rod, right? So this is the top view of the disc, but when I draw it on the or when I place it on the peg, it would look something like this. Yeah. So this is the front view of a circular disc being placed on a peg. So the problem says that there's a peg, let's call it source, and there are a set of discs being placed, let's say 3 discs being placed, and this is to be transferred to a destination peg. So, and it looks to be a simple job, but there are a set of constraints. So constraint number one is that you can pick only one disk at a time. You are not supposed to take the entire pile of disks, put it on the destination. That's constraint number one. The second constraint is that at no point of time you can have a scenario like this. We're talking about discs, and these discs are of varying sizes, right? So you cannot have a smaller disc below and a bigger disc above it, right? So this is something which shouldn't happen at any point of time, of you transferring the disc from the source to the destination. So with these two constraints, you're expected to transfer the set of discs from the source to the destination. Yeah, so that's it with the problem statement. We understand that since I have to move one disk at a time, I will have to be this would involve a series of steps, right? So let's see of how I would solve it in the simplest form. Yeah, so let's talk about a case when there's only one disk being given to us and it's on the source spec. So this is case one. I have one disk, the blue one, placed here from the source. Okay, it's a quite straightforward task because the only thing that I have to do is pick this disk and pull it, place it in the destination. So I am done, right? So I never used the auxiliary peg. Auxiliary peg was given to us to kind of hold some disk temporarily kinds, right? So I never used the auxiliary peg here because there was only one disk. So this kind of looks like the base condition of our recursion. Okay, so here we say this is the base condition or the terminating condition, where if you see only one disk, your problem is very, very simple. You just have to move that one disk from the source to the destination, right? Moving ahead, let's take the second case where the problem slightly gets bigger, tougher, where I have, let's say, two disks. Yeah, a bigger one is the blue one placed on the source, and above it is the red one. So let's look at of how do I transfer it. It's obvious that I cannot take both the disks from source, put it on destination, because it's not a load, and I have an auxiliary peg to help me here, right? So it's kind of obvious that I will use the auxiliary peg. So what I would do is I will take out the smaller peg, I will place it in the auxiliary peg, and that's kind of a temporary peg to hold the disc, and I will move this bigger one. I'll say, okay Baba, you go to the destination, and the chota, the red one which was on the auxiliary, will now move to the destination. So this is kind of the end of solving the problem, because you had two discs from the source, both the discs have moved to the destination, and it's kind of the same arrangement initially and the same arrangement after solving the problem, right? So this is one step ahead of base case, but we kind of figured it out for two discs. Okay, what could be the next complicated step of case 3? I now have 3 discs. So let me put a disc, red one here. Let me put a disc which is even more smaller than the red one. Yeah, probably this purple one. And how do I solve it, right? I want you to pause the video at this point of time. A couple of minutes, I'm sure you'll figure it out of how or what are the steps involved in transferring these purple, red and blue discs from the source peg to the destination peg, and probably you will use the auxiliary peg in between. Okay, I'm sure you've got the steps. So let's see if your answer matches with my answer. Yeah. So I would go about like this. I'll take the the smaller peg, put it in the destination. The purple one would go here, and I will have the red one which existed in source go out of picture. I will say, okay, you come here, sit in the auxiliary peg, right? So the smallest one is in destination. So what do? I cannot pick the blue one, put it on any other disk, because that's the violation of constraint. So two. So what I would do is take out the purple one, place it on the red one here in the auxiliary peg, right? So as you can see, it's kind of half the problem is solved, where the two discs are being placed in the auxiliary peg, and now it's time for me to take this bottommost bigger disc from the source, put it to the destination, right? So half the problem is solved. So let me solve the other one, where I will have to transfer the purple one and the red one to the destination, again with the same arrangement, right? So what I would do is I will take out this purple one. I'll say, okay, purple one, you please sit here for some time. Yeah. Meanwhile, I will have the red one move from the auxiliary peg to the destination. Yeah, this is the second largest disk, and above it would be my purple disk joining the destination peg, right? So fine. We have the arrangement or the problem being solved. So counting the number of moves, I'm sure you will figure out your answer and my answer is the same here, where we shifted the disk 7 times. Okay, 7 times totally to convert the initial arrangement to the final arrangement, right? So this is fine, but how do we take it ahead? As in, can we continue like this? Can we have case 4, case 5, and give all the steps to the algorithm? No, right? So the algorithm should talk about solving this problem for any given number of disks. Yeah, let's say there are n disks being given. I have to come up with an algorithm to solve it for any number of disks. And we will look at of how to do it recursively, right? So let's assume we have a set of disks. Yeah, I'll make it all of the same color here. So there's this biggest one, then one above it, a series of disks being given to us. I have no clue of how many disks are given. So let me say these are the n disks being given to us. Yeah, in our case, the value of n is 1, 2, 3, 4, 5, 6. Okay. So let's try solving the problem recursively. So how do I get all these 6 disks or n disks from the source to the destination? So if somebody tells me, or if somebody does the job of transferring the top n minus 1 disk, if I have them recursively move and go to auxiliary. I repeat, the first step would be to transfer the n minus 1 disk from the source to the destination. So let's take all this n minus 1, which is those 5 of them. Yeah, I put it in auxiliary. I now have just one disk on the source. So I understand moving one disk is the base case, yeah, or the simplest case, where I say, move this bigger one, place it here in the destination. Yeah, and this is still n minus 1 remaining as is on the auxiliary peg. So what should I do with this? So these n minus 1 is actually a smaller problem of the same bigger instance, correct? I was trying to solve it for n. I now have a smaller problem of solving it for n minus 1. So these n minus 1 disk is to be transferred from auxiliary to destination. But do we have an additional peg to help us out? Yes, and that is the empty peg, which is source. So the third step of the algorithm would be to transfer all these n minus 1 disks, recursively, and place it in destination. But let's see of how I do it. I do it using source as the auxiliary peg or a temporary peg, right? So you have the n minus 1 disk in the same order being placed from the auxiliary to destination, right? So we pictorially did it. I think we should formally write the steps that we said, right? So step 1, what did I do? I recursively moved n minus 1 disk from source to auxiliary, and there was a empty peg which helped me do it, so that was destination, right? And um, after I completed the first step, I had my auxiliary peg have all n minus 1. There was one biggest one in the source, so that would be my step 2, where I say move that nth disk, the largest disk, from the source to destination. Yeah, and the final third step, where I say step 3 is to again recursively move those n minus 1 which was here in auxiliary to the destination using source. Yeah, let's put that as a statement here. I say the last step is to recursively move n minus 1 disk from the auxiliary to destination using the source, because that was the one which was empty and it kind of held those intermediate steps, handled the intermediate tests, right? So this is kind of the recursive definition. Look at step 1 and step 3. There is a call to itself, and hence I say recursively solve the smaller problem of n minus 1 disks, right? And let's go ahead to convert this algorithm to a code. Yeah, we will look at a C code, which is according to the base condition that we saw, where I said base condition was to solve it if the number of disks is 1, which is basically n is equal to 1. And these 3 steps give me the case of solving it for all values of n being greater than 1, right? So let's go ahead to write the routine. Let me call it towers. And as you can understand, as we would have figured it by now, that the user, or there has to be an argument which tells me the number of disks for which the problem is being solved. So I have it as an argument. I say int n. I'm also being told the names of the pegs: source, destination, and auxiliary, right? So let's assume I am told what is the source. I am told what is the destination, and okay, I should also be told the auxiliary. So let's put the auxiliary also as an argument. Okay, so this is my prototype. The name is towers. There are 4 arguments: the number of disks, the source, the auxiliary, pekka name, and destination. So when you call it in your main, you could call it as we could actually give names to these pegs, right? Instead of say, I say they have to be characters. So I could say this is peg source A, and this destination is B, and there is an auxiliary peg C, right? So you could give character names to it, but yeah, the variables here are called source, auxiliary, and destination, right? So when you make a call to towers routine from the main, it would be something like this. So you say towers, you want to solve it for, let's say, 5 pegs, and you say the source is A, the destination is B, and the auxiliary peg is C. Yeah, so you could pass it like this, put it in single quotes because they would be treated as characters, right? Okay, so this is in my this is a call in my main function, but let's write the function here. Okay. Fine, let's put the base case. We are writing a recursive solution, so let's put the base case. So the base case is if n is equal to 1. There's only one disk. I understand I have to move it, right? So let's solve it here. But when I say move it, what does my C program do? Am I looking at an animation being done? Oh no, not obviously animating it, but probably I would put a statement onto the standard output using a printf saying this is the disk which is being moved, right? So every movement of a disk in my C program would be a printf statement. Okay, I repeat, every movement of a disk would be a printf statement in my C code. So let's complete this base case. So if n is equal to 1, I understand there's only one disk, and place that disk from the source, put it or dump it into the destination. So I'll say printf move disk 1 from source to destination. Yeah, here let me pass it as the value of those variables. So I will say source comma destination. Yeah, so I have a printf statement, and I understand when it's the base case I have nothing else to do, so make sure you return from the base case. Okay, after the base case I should go back or I should write the other set of steps. So yeah, the set of steps according to the step 1, step 2, step 3 that we wrote here, right? So I have to make a call to towers here, then have a printf statement in step 2, and again make a call to towers, right? So let's put that here in the else clause. So I say else, if it's not the base case, I will make a call to itself, or I will call towers again. But now I understand it's for lesser number of disks, right? So the number of disks is now n minus 1. I have to shift all those n minus 1 from the source to the auxiliary. Remember, just make a note of the order that I'm writing, because here in the definition, or it is source to destination using auxiliary. The step, the step 1 says from the source to the auxiliary using destination. Yeah, using destination. This is the first recursive call, and step 2, as I said, should be a printf statement. So let's print it. Let's say move disk. What did I say? I said move the nth disk, right? So let's go back. I said move nth disk from the source to destination, right? So let's put that as %d from %c to %c, right? So let's put values for all these placeholders. So this is n source destination. Yeah. After I have the printf statement, it's again one more call to towers, which is basically my third step. Yeah, let's go back to the algorithm. It said recursively move n minus 1 disk from the auxiliary to the destination using the source, because source was empty at this point of time, right? So let's do that here, where I say move the n minus 1 disk from where? Those n minus 1 were actually now in auxiliary, right? So I have to take it from auxiliary, put it to destination. That's where it was expected, the final answer. But who's that temporary variable or khali peg that's helping me out? That is the source, right? So That's the second recursive call, and this closes my else. Let me also close my recursive routine, because I understand I've written the base case, I've written the recursive case, and I have my routine towers complete here. Okay, so this would be my C code, which does the job of solving the towers problem, right? The way you call it in your main would be to say main, a set of steps to read what the value of n is, yeah, from the user, and you will probably pass that value n here, and you will see a series of printf statements as an output, and these printf statements are the number of steps, right? We will quickly jump to understand of how this recursion would be handled, let's say for 3 disks, right? We saw of how 7 movements are expected when I'm solving the problem for 3 disks, as in there should be 7 printf statements. So let's understand that here with this recursion tree. Okay, so here, okay, it's called tower, but we called it towers there, but it's the name of the routine is not an issue. But look at the arguments that are being passed. I say, yeah, so I have towers of 3, source, auxiliary, destination, right? So as I said, this would be basically tower of 3 comma the source, which is A, auxiliary, which is C, and destination, which is the peg B, right? So what would happen is towers of 3 will now make a call to towers of 2, n minus 1, and that will again make a call to towers of 1 comma or the other arguments, right? So the first printf statement that would happen would be this, which says move 1, the smaller one, from the source to the auxiliary, right? So this would be the very first statement on the screen, and after this is done, it will go back to this call. This is done, so it will go back. So if you could remember, we are done with step 1 of this call, and the second step would be to do this printf statement. So this will be the second printf statement, yeah. And after the printf statement, there is the second call to towers of a smaller size of 1, and that will give me a printf statement. So this is the third printf statement. So as you can see, after the 3 printf statements, the entire problem of shifting 2 disks from the source to the auxiliary is done, yeah. So we have that bigger third disk to be moved from the source to the destination, and this would be my fourth printf statement on the screen. And then would be the call to towers of 2, and it moves down. This will be my fifth printf statement. This is the sixth printf statement, and this will be the seventh printf statement, right? So what we see trying to see is to understand of how recursive calls are being made for one instance of a call to the routine towers, where the number of arguments is 3, right? So there are 7 steps. Let's continue to understand if this number of steps has any relation with the number of disks on the problem statement. Yes, so let's make let's say number of disks, and let's say number of moves or number of printf statements that you see as an output, right? So we know the simple case where there's one disk, I will just have one move, right? But we saw when there are 2 disks, I will have 3 moves. The smaller one goes to auxiliary, the biggest one goes to destination, and the third step of the smallest one going to the destination, right? And the number of disks being 3, we saw just now that there are 7 steps, yeah. For this, you will figure out a series of steps. You could do it as an exercise of solving it. You will see that the number of steps is 15. So there's actually a pattern being followed here, right? Then the pattern is something like this, right? So it would be 2 power 4, the number of disks, 2 power 4 minus 1, 16 minus 1. And very similarly, if you could backtrack, so this will be 3. So I'm solving it for 3 disks, so it is 2 power 3 minus 1. And this is 2 power the number of disks. How many? 2, right? So it's 4 minus 1, and hence you have the answer 3, right? So in general, or let's do it for 5. So 5 disks, it should be 2 power 5 minus 1, right? So that would be 32 minus 1, right? So you get an answer that there are 31 moves involved when you're solving this problem for 5 disks. So in general, when you're talking about n disks, your number of moves will be 2 power n minus 1. Okay, it's a power of it's kind of exponential, 2 power n minus 1, right? Why is it 31? It's because when you talk about towers of 5 disks being solved, it is 4 disks being solved, which involves 15 steps, and there is one step of moving the fifth largest one to the destination, and again there are 4 disks from the auxiliary peg to be moved to destination, which again has 15 steps. So you kind of have that 15 plus 1 plus 15, and hence it turns out to be 31, right? So we could also understand it like that, but the general formula is if there are n disks, the number of moves would be 2 power n minus 1, right? I would want to conclude this video or this understanding of all about Towers of Hanoi with a demo which is actually found on one of the virtual labs of IIIT Hyderabad. So let's see of how it visualizes the problem for 3 disks. So let's have the animation start. So here you could see the program which is very similar to what we wrote, but probably the arguments are slightly different, and it's coded with numbers being given as names to the source, destination, and the auxiliary pegs, right? So if you could see here, you will have numbers coming up, but we gave them names as ABC, right? So this gets us to solve, or lets us see of how 7 steps are involved in solving the problem of 3 disks, right? So the red color here shows me the executing statement. So as you can see, there are calls made to the routine Hanoi, and this is the first move. And then the next one and the third one would be to place the smaller one to the last destination one, right? So it's now the first call to towers is over. Half the problem. We could also visualize Towers of Hanoi problem as an excellent example of binary recursion, just the way as the Fibonacci series, right? So because jumping back to the routine that we have, there is a call to towers twice, right? So it's an excellent example of binary recursion, right? So you could see it here as well. Hanoi is the routine, and it's called twice here in the execution, right? So let's continue. So as you can see, you will have a series of function calls to itself, and finally you have the problem being solved, right? So you have the entire arrangement of 3 disks from the source to the destination, and please remember, none of the constraints are violated here. I always moved 1 disk at a time, and at no point of time you had a bigger one rest on a smaller disk, right? So I would want you to try out this animation or the simulation thing on the virtual lab, and also try the coding for the Towers of Hanoi problem. Yeah, that's it about towers. Thank you.